Students, we are going to discuss about the performance test on Kaplan turbine, Francis turbine and impulse turbine. The photograph shows a Kaplan turbine setup used in the laboratory, and this figure shows the pipe through which the water enters into the turbine. We can determine constant head characteristic curve of a turbine as well as constant speed characteristic curve of the turbine. When you want to determine constant head characteristic curve, the valve position is not altered. So you can see the water enters the turbine through this pipeline. There is a valve to change the discharge of water. So when you want to run the turbine, when you want to conduct the experiment under constant head, this valve position is not altered. When you want to run the turbine at a constant speed, then the valve position will be altered depending upon the loading. See, the turbine is loaded using dead weight placed on the pan. When the turbine is run under constant head, as the load is removed or added, the speed of the turbine changes. So we have to determine the speed of the turbine at each and every loading level when you want to run the turbine at constant head. When you want to run the turbine at constant speed, the speed of the turbine should be kept constant at its rated level. So we have to change the input conditions. As the load is getting changed, the speed will automatically vary, but we have to control the speed, so by altering the valve position. So for conducting the constant speed test, we have to change the valve position depending upon the load. For conducting the constant head test on the turbine, the valve position is not altered. So this turbine receives water through this pipeline. There is a orifice meter placed inside the pipeline to determine the discharge. The area of the opening of the orifice meter is A2, and the area of the pipeline through which the orifice meter is kept is the A1. So when you want to determine the constant head characteristic of a turbine, these are the graph that you have to draw after completing the experimentation. When you want to determine the constant speed characteristic of a turbine, this is the graph you have to draw after completing the experimentation. So let us see how to find the efficiency of the Kaplan turbine. To determine the pressure of water entering and leaving, there are two pressure transducers used in this experimental setup. So the head of water acting on the turbine is measured using the reading shown by these two pressure transducers. So the head of water acting on the turbine is the addition of suction head and delivery head. The discharge is found out using this formula. Since we use orifice meter for determining the discharge, the A1, A2 refers to the area of the pipeline in which the orifice meter is placed, and A2 is the area of the opening of the orifice meter, and a manometer is used to determine the pressure difference between the two sections of the orifice meter. So rho m is the density of the manometric fluid. If the mercury is the manometric fluid, you have to substitute the density of mercury here, and rho is the density of the flowing fluid, and H is the level difference of the manometer, level difference of the manometric fluid in the manometer. So that is the H. So the input power is determined using the formula WQH, where W is the specific height of the flowing fluid, Q is the discharge, and H is the head. The output power is given by 2 pi NTP 60,000, and efficiency is output power by input power. This figure shows a experimental setup used to determine the performance of a Francis turbine. A venturimeter is used to determine the discharge. There are two pressure gauges used to determine the pressure of water entering the venturimeter and pressure of water at the throat of the venturimeter. So this is shown, the venturimeter shown in this figure. A1 is the area of the venturimeter at the entry, and A2 is the area of the throat of the venturimeter, and Z1 and Z2 are the elevation of the entry to the venturimeter and throat of the venturimeter. And these two pressure gauges are recording the pressure of water entering the venturimeter and the pressure of water at the throat of the venturimeter. The formula to be used here is written here. A1, A2 are the area of the venturimeter at the entry and at the throat, and P1, P2 are the pressure gauge reading that records the pressure of water at the entry to the venturimeter and at the throat of the venturimeter. Z1 minus Z2, okay, is the level difference of the entry and throat of the venturimeter. The input power is WQH, where W is the specific weight and Q is the discharge and H is the head. The output power is 2 pi NTP 60,000, and efficiency is determined by output power by input power. We can also determine the performance characteristic of a impulse turbine. We can run the turbine under constant head as well as under constant speed. As I already told you, when you want to determine the constant head characteristic of the Pelton turbine, the valve position is not altered. As the load changes, the speed changes, we have to record the speed. When you want to run the turbine to determine its constant speed characteristic curve, we have to change the valve to bring the speed of the turbine at its constant level. So a venturimeter is used to determine the discharge of water, and there are two pressure gauges which are attached to the venturimeter to determine the pressure of water at the entry and the pressure of water at the throat of the venturimeter. The venturimeter is kept horizontal in this case. So the Z1 minus Z2 value will be 0 when the venturimeter is kept horizontal. We are using this formula to determine the discharge of water through the venturimeter. The input power is WQH, output power is 2 pi NTP 60,000, and the efficiency is output power by input power.